So just to give a quick recap of what we have done in the last class. Okay. Now again, what we are really doing, or what we are trying to do here, is to slowly build up those building blocks. Okay. Just like what we have done for our in the combinational circuit design, we were slowly one step at a time. We were building those building blocks or the modules, and then we were basically applying those modules to build more complex circuits. In exactly analogous to that, we are doing the exact same thing here. We are trying to build up those various building blocks, okay, understand them, apply them, and eventually use them in the design of more complex circuits. Okay, so that's the idea. So in the last class, towards that, we talked about the design or the applications of D flip-flops, right? We talked about the triggering mechanisms for these flip-flops. You have two different ways that you can trigger them. Trigger as in your output is when I say trigger, that basically what I'm trying to say here is when does your output of the flip-flop respond to the input, right? Again, that is synchronized with the master clock. And so you can design your flip-flop so that it triggers at high levels or low levels, which are called the level triggered flip-flops. And you can also design flip-flops through what is called the master-slave configuration. You can also construct flip-flops that can be triggered at the edges. It could be a rising edge or it could be a falling edge. Okay, and this is exactly what we have done in the last class, or and then the other aspect of the last class was we looked at how do we apply them in the design. Okay, in what different ways we can apply them. And of course, as the name suggests, for the D flip-flop, these are data flip-flops, right? So I can basically use them to store data. And in the last class, or in the last few classes, we looked at the construction of a register. As temporary, you can think about a register as a temporary memory location that can be used to store data. You can load data as a parallel load operation directly from in a single clock pulse, synchronized with the clock pulse. You can load it in a single clock pulse into all of those into all of those flip-flops constituting the register from the data bus. That's the parallel load operation. That's called the parallel register. We can also do serial operations, and serial operations are also very important, right? Because we are streaming all the time. You stream information, you send out information. Like for example, when you're trying to connect a Bluetooth device, right? So let's say you're building something, and or if you want to uh, uh, talk using Bluetooth, or if you want to display a signal from some circuit that you've constructed, and let's say the circuit has a sensor, and you want to display that wirelessly to a computer using a Bluetooth connection. Okay, and in that case, again, you are trying to stream the data one bit at a time, right? It's basically you're working with serial data in that case, and in that case, you need to have these serial ports, serial registers that can help you in obtaining that data. And towards that, we looked at the design of a serial register, okay, again using D flip-flops in the last class. And we also looked at the design of a universal shift register, okay, that can do both serial operations as well as parallel operations. So it can do both, parallel load operations, shift right, shift left, and memory operations, right? So this is something that we have looked at in the last class. Okay, and towards the end of the last class, we also looked at a slight modification to a D flip-flop, to an edge-triggered D flip-flop. All we have done, so modification looked something like this. So let's pick it up from there, and let's examine what kind of a circuit we have derived in the process. Okay, so the modification was simple. You have basically a D flip-flop. How I got the modification, we'll see on what basis I've done the modification in the next few classes. But for now, let's say just just accept that this is something that I've come up with. Okay, so this is a negative edge triggered flip-flop. So that's where I apply my clock. That should enable input. And all I've done is basically use a OR gate here. In other words, basically I have implemented a simple combinational circuit, introduced a simple combinational block over here, introducing two new inputs to this system. One was the J input. Again, it features a feedback from the output of that flip-flop. Okay, and the other one was the K input, which is primed here or complemented before it goes into the AND gate. And this one again was the other input of for this particular gate was from the output of the T flip-flop. So this is what we have done, and we want to analyze it. Now again, and this is exactly the procedure that you will be following when you're doing your homework assignment, the homework 7. Okay, the way I would analyze it, I would always, derive the, or at least I would keep the input-output characteristics of the modules I have already analyzed handy in this analysis. Okay, now this is something that I already know. I have analyzed this. We know how this flip-flop works, the D flip-flop works. So that information is there. Okay, and I would use that information in the analysis here. I have two new inputs, J and K, and I would express my D because the output of this combinational block F, let's say, is nothing but D. And what is F here? F is, if I follow the inputs and follow these inputs, what I have is J Q prime plus K prime Q. That's it. And I know how the D flip-flop works, and we derived this in the last class. This is what we have derived it for the characteristic table of this flip-flop, of this, let me call this JK flip-flop. This is a new flip-flop that is derived from the D flip-flop here. And how does that look? So I have two inputs, J and K. I have an intermediate input D. Again, for all said and done, what I'm really interested in is because if I enclose this in a box, the inputs to the blocks are J and K, and the outputs are Q and Q prime. Right. What happens inside, I'm not so much concerned as long as I know what the input-output characteristics are and something that I'm trying to derive it. Okay, in this case. Now, the inputs are J and K. This is the intermediate input D. So let me place that there because that would help me with the analysis. Then I have Q and Q prime, and the output is basically Q. Now, because I want to know what happens in the next triggering instance, I would represent that as the Q2T plus 1. What it means is if I apply an input on my flip-flop, okay, when the flip-flop gets triggered in the future or in the next triggering instance, how did the output of the flip-flop change given this input? Okay. So I'm always looking at what is happening in the next triggering instance. Okay. All right. So we chose different values, just like you would do in a truth table. Although this is still a characteristic table because you have the dependence of the outputs. Okay, and when I apply 0, 0, plug the values here and note down what you get for D, or in other words, F. F is nothing but D, right? So J and K both zeros. That goes to 0. That was Q. So in other words, I'm basically taking Q, applying back to D, something that we have already seen. And then, so when I'm applying the same input or same output as the input in the next triggering instance, because my output follows the input for a D flip-flop, that remains, the output does not change. That means it just keeps the same value without it being changed. 0, 1, 0, 1, again you plug in these values here. 0, 1, that means I'm applying a value of what? J is 0, K is 1, K prime becomes 0, that's 0. So I'm applying a value of 0 on D. That means in the next triggering instance, output follows the input. So whatever was there before, it gets overwritten with 0. 1, 0, if you recall, that was q plus q prime plus q prime plus q by Boolean identities is 1. So that's a 1. In other words, I'm applying a 1 on my D input and waiting for the next clock instance. So in the next clock instance, my qt plus 1 follows D. So that's 1. And finally, we have 1, 1. Apply 1, 1 here. So I get f equals 1 times q prime is q prime. 1 on k, that means k prime goes to 0. That's 0. In other words, I'm applying a q prime on D, q prime of t on D. So what happens in the next clock instance? In the next triggering instance, output follows the input. So qt plus 1 becomes q prime of t. Now what does this mean really? Because that's important. We have seen this before. Okay, particularly for the SR flip-flop, we had seen those states before, but we have not seen this before. What does that indicate? What that indicates is, if I apply a j and k of 1, 1 on this flip-flop, okay, what I'm doing is I'm applying a value of q prime of t on the flip-flop, or in other words, if q was 1 to start with, or q was 0 to start with, that means when I place j and k both once on j and k, then I'm applying a value of 0 on my D. So in the next triggering instance, my qt plus 1 goes to 0. Goes, let me see, what did I say? Okay, maybe it's much better to show it in the form of a truth table, in the form of a timing diagram. Okay, let's actually do this. So let's say this is my clock. So timing diagrams are very handy, especially for these situations. So again, these are my active edges because this is a negative edge triggered flip-flop. So these are my active edges, the negative edges. Okay. Now I'm plotting my q of t here. Okay. All right. Now I'm plotting just for the situation where my j is k equals 1. Remember, for the SR flip-flop or SR latch, the NAND or the NOR version of the latch or the NAND version of the latch, the j equals k equals 1 gave us the forbidden state, right? If you recall, that's what we had. For the improved version of the NAND latch or the NOR latch, that's what we had obtained. Here, what kind of a situation I'm landing myself in? Let's see. So what does this mean here? If q was 0 to start with, now this is my next triggering instance, right? That's where I have qt plus 1. So if I'm looking at, if I'm standing here at this time, that's my qt plus 1, that corresponds to my qt plus 1 in the next triggering instance. And according to this truth the characteristic table, you can see that in the next triggering instance, whatever was there before it was 0, that gets complemented in the next triggering instance. So q prime of t. So it was 0, that means q prime of t of 0, q of t of 0 becomes 1 on the next triggering instance, because I'm complementing that in the next triggering instance. Okay, so that's 1. That becomes 1. Okay. Now I'm standing here. My next triggering instance. Now the next qt plus 1 is basically this part. So I'm standing at 1. So this is my next triggering instance. Again, that gets complemented according to this characteristic table, and so on. The process continues. So at every triggering instance, my output of this flip-flop is getting complemented for j equal to k equals 1 condition. And this is what I get. And this particular state is called the toggle state because it's toggling between 1 and 0. Right? With every clock pulse, my output changes from 1 to 0 or 0 to 1. So that's the toggle state. So now we have derived a new state called the toggle state. Okay. All right. Now, does that make sense? Any questions on this? If you look at this pulse, this is also a series of these pulses, square pulses, and with respect to the clock, what can you say about that? The output Q in this case, with respect to the clock, what can you say? What do you observe there? Anthony, what do you think? Do you see any difference? Are they the same? Obviously, they're not the same, right? That's my clock. That's what I'm getting for Q of t. Toggling with every active edge. Still a square pulse. However, something different compared to the master clock. And let's talk about the difference in terms of the frequency of the clock frequencies. So what can you say about this? Let's say the frequency of the clock is Fc, the clock frequency. What can you say about the frequency of Q of t? This frequency. Are they the same? Obviously not. If FQ, let me call it FQ, is FQ larger than FC or FQ less than FC? Correct? Less, right? And it's basically half. So FQ, in terms of the clock, it's basically FC over 2. The frequency gets halved. This is switching. It halved the frequency of the clock. Okay, so that's good. Now, instead of representing a JK flip-flop with all of this, I can now basically symbolically represent a JK flip-flop just by using a rectangle. So that's my J, that's my K input. Q, Q prime. I have 2 inputs for this flip-flop. That's the clock. And 2 outputs, Q and Q prime. So that's my JK flip-flop. That's a symbolic representation for a negative edge triggered flip-flop. That bubble represents a negative edge triggered flip-flop. Okay. All right. Now, what can I do with this? What is the point of having a toggle state? Right? Can I use it for something? So let's examine this circuit, and then we will see what we can use it for. So what I'm going to do now is I will take 4 of these flip-flops, 4 of these JK flip-flops, and connect it in this format. So that's my first. That's my second flip-flop, third, and fourth. Okay. Let me call that JD, KD. That makes it QD. QD prime is there. I'm not just showing it, but it's there. Let me call it JC, KC, QC, JB, KB, QB, and finally JA, KA, QA. And what I'm going to do now is I'm going to basically place them each of these flip-flop in the toggle state. And the way I will do that is basically by shorting J and K inputs and applying a value of 1 on my J and K values, right? That basically configures each of these flip-flop in the toggle state. That's placing a 1 on this line. Okay, and each of these is a negative edge trigger flip-flop. Okay. So now I have configured each of these JK flip-flop in the toggle state by combining J and K values and tying these up and applying a value of 1. And for the clock, I will apply the master clock for the first flip-flop. That's the master clock applied to the first flip-flop. And for the subsequent flip-flops, I would use the output of one of the flip-flop, apply it as the clock input to the next flip-flop. Same thing here. QC is being applied as a clock input to the next flip-flop. QB the clock to QA flip-flop. That's it. And I'm going to monitor the values for with each clock pulse. I'm going to monitor the values of, so these are the outputs, right? So QD, I'm interested in monitoring how the QD, QC values, QA, QB, and QA values change. Those are the values I'm interested in. With each passing clock, with each active edge, how does my values on QA, QB, QC, and QD change with respect to the master clock? All right. Now, let's to understand this again, let's draw the timing diagram for this. So let's do that here. So that's my master clock. Again, whenever I'm drawing the timing diagram, I start with the clock because the clock is the one that's providing the timing information in the first case, and I want to reference everything, the timing information about rest of the circuits, everything against the master clock. So that should be the practice. Okay, so that's your clock. So I'll draw this. I start with this clock, master clock. Identify the active edges. That's the next step that you will be doing when you're drawing the timing information. Is in this case, obviously, because these are all negative edge triggered flip-flops, I would identify the edges, the negative edges, as my active edges or my triggering instances. So that's my clock. That's my master clock. And let me plot QD first with respect to the master clock. So that's going to be my QD. Okay. Now I will identify my edges. So these are my edges. These are the active edges, the edges where my flip-flop gets triggered, or the output of my flip-flop gets triggered. Now QD we already know, right? The QD, okay, let me just put down these guidelines so I know exactly where my triggering instances are for QD. Because for QD or the JD, KD flip-flop, the clock, the master clock is directly applied as the clock to that flip-flop, and we have configured each of these flip-flop as it in the toggle state. So if my output is assumed to be 0 to start with, at time t equal to 0, then these are my triggering instances. So basically my output toggles at each active edge. So these are my active edges. And that's the waveform I'm going to get on QD. Okay. Now let's draw QC. That's going to be QC. Now, for QC, my QD is the clock. I'm applying the QD as the clock to my QC. So now, this signal is the clock. I will identify the active edges for that flip-flop. These are the active edges. The falling edges are the active edges for my JC KC flip-flop, and then I will draw the guidelines for them. So these are the guidelines where my flip-flop gets triggered. Again, I assume that it's to start with, everything was zeros. So that's the next triggering instance. So it's toggles, QC toggles, toggles, toggle, toggle, toggle. Now let's draw for QB. Again, QB, QC is the clock. So these are my triggering instances, my guidelines. Again, QB remains 0 until the next triggering instance. Toggles, toggles, so on. And finally, we have QA. QA, QB is the clock for the JAK flip-flop. That's my guideline. And this is what I'm going to get. So that's the timing diagram for each of my outputs for this flip-flop. So what can I gain from this information, right? What do I really get? Now, in terms of frequencies, we already know my QD is toggling at a frequency FC over 2. If this is FC, that's FC over 2. QC, with respect to the master clock, what is the frequency? Halved again, that means FC over 4. QB, the frequency is FC over 8. QA, frequency is FC over 16. So you can implement a frequency divider with this circuit. About that one application. Why do we need a frequency divider? We'll get back to that in a few minutes. Okay. And what else can we use these for? Again, as you can see here, this particular signal, each of these signals are on for a set period of set number of clock cycles. This is on for a set clock cycle period, or set number of clock cycles, set number of clock cycles, and off for set number of clock cycles, right? For example, if I ask you for how many clock cycles is this signal on, you can check, right? 1, 2, 3, 4. So for this particular signal is on for 4 clock cycles. Okay, and we'll take an example of about situations where we can actually apply this as timing signals. Like we talk about timing signals, we have again when we talk about a large complex system where you have multiple units connected together. Now, module 1 or system 1 may take n number of clock cycles to finish an instruction. That's the speed at which it's operating, versus a system 2 may be taking n plus 2 number of clock cycles or more number of clock cycles. And if I want to communicate between these two, that means I need to wait a set number of clock cycles before I can, communicate with that other device. So I need to have some kind of a timing signals, some way of generating timing signals in my design, so that I can apply these timing signals and synchronize the operations of all of these interconnected systems. Okay, all right. So these circuits can provide you with that timing information. These circuits can be able to or used to generate those timing signals. Again, this is just one example, okay, of doing that. And what we have basically synthesized here, you will actually know what this can also do. Now, if I note down the values in terms of a table with respect to the clock, let's say this is my clock signal, and I'm noting down the QA, QB, QC, QD values. instead of looking at them as data or as waveforms, I'm just writing down the values of these on QD, QB, QA, QC. Okay. All right. With respect to the clock cycles, so let's say on the 0th clock pulse, which responded, that's the 0th clock pulse. That's the first clock pulse. That's my 0th clock pulse. Everything was at 0. Right. So QA value is at 0, QB at 0, QC at 0, QD at 0 as well. On the first clock pulse, when I say the first clock pulse, I'm talking about the first triggering instance. That's my first triggering instance. My QD is risen to 1. That means my QD value was toggled to 1. Right? On the first clock pulse, what is the value on QC? My QC is still 0. There's nothing here. QB is still 0. QA is still 0. Right? So rest of them are all zeros. So that's on the third clock pulse. I'm sorry, on the second clock pulse, which is this one. My QD went from 1 to 0. So I've registered a 0 on my QD. My QC went from a 0 to 1. That means I've registered a 1 on my QC. My QB is still 0. QA is still 0. So these are still zeros. Right? On the third clock pulse, okay, let me just number them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. On the third clock pulse, I'm going, my QD went from 0 to 1. That means that's a 1. My QC remained at 1. That's a 1. My QB is still at 0. QA is still at 0. So these are zeros. The fourth, which is here, QD again toggled to 0. That goes to 0. QC toggled to 0. That also went to 0. QB goes from 0 to 1. So that's a 1. And that's still at 0. And so on. So what do you see here? If I note down the values on my QA, QB, QC, and QD, what do I get? With respect to the master clock, do you see anything there? What I'm really getting is a count of the clock, a count of the number of clock pulses elapsed. If I'm more clock pulses elapsed, right? It's basically counting my QA, QB, QC, QD values are basically counting the number of clock pulses that have elapsed. That's why we call that circuit a counter. It's nothing but a counter. A counter can be utilized to count the number of clock pulses, count the number of events, as a frequency divider, in this case, as a timing signal generator. So you can have multiple applications for a counter in your device design. Okay. Now, on each of your computers, you have the clock, right? The clock that shows time. That's basically constructed through these counters. Now you have a clock for your computers, of course. Your clock is in gigahertz, right? And I need to get from gigahertz. Basically, you're counting seconds, you're counting minutes, you're counting hours, right? That means I need to count down. In other words, I need to divide the frequency so that I can get the seconds, minutes, and hours count from your master clock, right? So now you need to have some kind of a frequency division, and you can figure out how many times I should, or by what factor I should divide my clock frequency to be able to count hours, minutes, and seconds. That's how you're able to, your computer is able to display time and count and count forward in time, right? Using your master clock as the signal. Okay, let me pause here and let me see if you have any questions so far. That's a good point. That's a good comment. But you should do this exercise anyway. By what factor you should be able to, because again, from gigahertz, you have sufficient resolution to be able to count in seconds, minutes, and hours, even if you're counting by 60s, right? So it will be a good exercise if you actually figure out and see by how much you should reduce, by how much you should divide that master clock frequency to be able to count in these seconds and so on. Okay. So that is your counter, and it is called. So what is the maximum count that you can count with? Use this to count. So basically, it goes on the 15th clock pulse. I would basically be counting 1, 1, 1, 1. On the 16th, what's going to happen on the 16th? So I can count from 0 to 15. What do you think will happen on the 16th clock pulse? This is pretty straightforward, right? For QD, because it's basically toggling 0, 1, 0, 1, 0, 1. So if it's 1, then on the 16, that's going to go to 0. There's no doubt about that. So on the 16th clock pulse, it turns out that you will basically end up with 0, 0, 0, 0 again, your initial count, and then it starts counting up again. So that's why. So because we have a 16 total count, 0 to 15, 16 unique counts. So this particular counter is also called modulo. So we express the counter in terms of how many unique counts you have. It's a modulo 16 counter. Okay. Now, if I use an additional flip-flop here, this is a counter that is constructed by using 4 flip-flops configured in that way. I can also add another flip-flop here and then just drive that output at the clock for the additional flip-flop. In which case I will get a modulo, how many count? When I have 5 flip-flops, my count increases by factor of 2. So with 5 flip-flops, I'll end up with a modulo 32 count or counter. So basically with every addition of a new flip-flop, you're increasing the count by a factor of 2. So in general, if I have n flip-flops that is used to construct my counter, then I would basically end up with a modulo 2 power n counter. So that's how you can increase your count. All right. Now this is an up counter, as you can see, because it's counting up 0, 1, 2, 3, 4, 5, and so on. Now, how do I construct a down counter? Any comments on that? Any suggestions on how do we go about constructing a down counter which starts with 1, 1, 1, 1 and starts counting down? Well, remember that you also have Q prime. For every flip-flop, you also have these primed quantities. And I can also monitor my Q instead of Qs. I can also monitor Q primes, right? When I monitor Q primes, I'll get a modulo down counter because it's counting down. Start with 1, 1, 1, 1, starts counting down. Okay. So that's how you get a modulo 16 down counter. So you can do an up counter, you can do a down counter, and so on. All right, so that's good. Now let's take a quick example of where I can apply these timing signals, just to give you some kind of a sense of, in your system design, how do I apply a timing signal, just to give you a slice of that. So let's examine this particular circuit, or this particular situation, where I have two registers, two shift registers, all right, two 4-bit shift registers, and what I want to do now is I want to copy the content of one 4-bit shift register into the next 4-bit shift register. Without destroying the content on the first register, I want to copy it into the next register and store it. Okay, so this is what is the situation. So I have, that's my first shift register that contains some data. That's my second. I want to shift the contents of this register into this new register, okay, or copy the contents, and making sure that my contents in this initial register are not overwritten or not destroyed. Okay, so for this operation, this is what I will do: a simple circuit that can be configured this way. So again, as we have already discussed, each of this block is nothing but a D flip-flop, and these are all internally connected. That means if I show the clock to one flip-flop, that means that clock is internally connected to each of the flip-flop. Okay, same thing here. All right, and because that's the shift register, again, although I do not show the explicit connections, they are there. It's basically shifting one bit to the right with each active edge. Okay. All right, so that's the input to the flip-flop, to the register. And because I don't want to lose the content, what I'm going to do is I'm going to shift back into the same register. Every time I'm shifting it, the output is being fed back into the same register. Okay. All right. And I'm going to shift the contents of this flip-flop, start shifting into this flip-flop. Okay. So that's my A register. Let's say that's my B register. Both are shift right registers, and that's the output of this particular register. Now I want to make sure that once I shifted the contents of this into this, I want to keep them. I don't want to override this contents in this register anymore. Okay. Now let me ask you now, if I want to do this, of course this is my clock. If I want to do this operation, okay, how many clock pulses should I be applying to these registers so that I can shift a 4-bit data value here into this register? How many clock pulses should I be applying there to those registers? Let's say some value is here, 1, 0, 1, 1. These are all cleared to start with. I want to shift this value into this register, 1 bit at a time, synchronized with the master clock. How many clock pulses would it take for me to shift the value of A into the B register? On the first clock pulse, this 1 gets shifted to this position, this 1 gets shifted here, 0 gets shifted here, 1 gets shifted here. This outgoing 1 is again being shifted back here, right? I have a 1 here. On the second clock pulse, this 1 gets shifted here, this 1 gets shifted here, 0 gets shifted, 0 gets shifted here, and so on, right? With every clock pulse, I'm shifting 1 bit towards the right. If I want to shift the 4-bit number, that means the number of clock pulses I should be using is basically 4 clock pulses, right? So in 4 clock pulses, my number is shifted. Now, after applying 4 clock pulses, I need to make sure that I'm no longer shifting it anymore, because if I do, then my data is being shifted out of this register. I'll be losing the data. That means I need to stop shifting after 4 clock cycles. So that means I need to design a timing signal that would be on for 4 clock pulses and off subsequently. So examine this circuit. So instead of applying my master clock directly, this is one way of doing this. This is my clock signal. This is the continuous train of these pulses being applied here. And that is my shift control signal that I'm applying here, shift control. What is my shift control? A signal that looks something like this. This is my clock. My shift control is a timing signal that is on for 4 clock pulses only. So let's say again, these are all negative edge triggered flip-flops. One, two, three, four. So I design my timing signal so that it's on for 4 clock pulses. Now, this is an AND gate. It's an AND gate between this clock and the shift control. So what is the clock being applied to this particular signal, or to this particular circuit? That would be basically, this is 1, because this is the AND operation between the clock and this particular signal. As long as it's 1, this signal is being replicated. So I get something like this. In other words, I'm applying a clock signal, exactly 4 clock pulses to my registers, so that once the content is shifted into this register, after the fourth clock pulse, of course, my clock is now disabled. That means I'm no longer shifting anymore the content, and the content is preserved, and that's it. So that's again just an example of where you can apply these timing signals for synchronization operations. Okay. All right. So that's just an example. Now let's go back to the, yeah. Now, when you design the flip-flops, the question was, are we using only the negative edges or both negative and positive edges? Now, when we design our flip-flops, you design it as a flip-flop that triggers on the negative edges or positive edges. Okay, let me correct myself. When you're designing a flip-flop, you design it either as a flip-flop that gets triggered on the negative edges, or a flip-flop that gets triggered on the positive edges, not both. So it depends on how you design your flip-flop. Okay, but if you design it with negative edge as a flip-flop that gets triggered on the negative edges, then it's called a negative edge triggered flip-flop, and it gets triggered only on the negative edges. So it does not see the positive edges. For example, here, these are my positive edges, and my flip-flop does not get triggered during those positive edges. But I can definitely design flip-flops that can trigger on the positive edges as well. Does that answer your question? So I need to specify what kind of a flip-flop I'm working with so that I can draw my timing diagram. Okay. All right. So, okay, so that's good. So we talked about this. Now, what about situations where we want to get an arbitrary count? Arbitrary count as in, for example, let's say you want to count from, 0, 0, 0, 0. Let's say you want to form a decade counter, not a not an hexadecimal counter. A decade counter, as in you start with 0, 0, 0, 0, and you count count to 9, and then you go back to 0, 0, 0, 0, and so on. So you basically your count is basically 10, right? Decade counter. Can I configure or can I apply my ripple counter or the counter that we just designed to obtain a decade counter? Now, by the way, the counter that we just designed, right? That's also called a ripple counter. Why it's called a ripple counter? Because the way we have designed it, the clock of one flip-flop is fed at the clock to the next flip-flop. So my outputs essentially are getting rippled through these different stages, right? So my clock gets rippled through. My clock is only applied to one flip-flop, but then the effect of this clock is rippled through these connections. That's why it's called a ripple counter. Okay. Now let's try to design a decade counter that can count from 0 to 10 or 0 to 9, getting me a count of 10. Now, how do we do this? Or for example, for that matter, if I want to count some random count 0, 0, 0, 0 to 5, and then I want to reset that and count. So every time I want to count from 0 to 5, reset it, count back from 0 to 5, and so on and so forth. So I want to make it flexible. Okay, how do we design that? Now, although again, you must have realized by now that all of these circuits that we represent, these are all active circuits. These are made of active elements, right? These are made of transistors. These are all active elements. They have to be powered up. I do not show those connections explicitly, but each of these circuits have to be powered up with VCC and ground, because these are all powered by transistors. I do not show them. And likewise, we also have additional inputs that can be designed. For example, a preset and clear inputs. So let's look at an example of a flip-flop that contains these inputs. So let's look at the JK flip-flop, a negative edge triggered JK flip-flop, my J, my K, that also contains these preset and clear inputs. Call that preset. Let me call that clear. That's my Q and Q prime. Now, what it means is that the way I've represented these with this bubble, this representation means that these are active low inputs. These are active low inputs. In other words, these inputs become active only when I place a low value on these inputs. For example, if I want to make preset to be active, then I would place a 0 on my preset input here. Likewise, on my clear input, if I want to make the clear input to be active, I would place a 0 on my clear input. Right? So these are active low inputs. And these preset and clear values or inputs take precedence over my J and K values, or the precedence over the operation of the flip-flop. In other words, if I, let's say, if I place the preset and clear to be ones, then of course my flip-flop basically operates as a regular JK flip-flop. Okay. On the other hand, if I go back and then at some instance of time, let's say I place preset to be a 0 and clear to be a 1. My clear is not active because I'm placing a 1 on my clear. My preset is 0, that means my preset is clear. Then it takes the precedence and forces the output of my Q to be a 1. Okay. And it can be done as asynchronously with respect to the clock. In other words, it does not have to be timed with the clock. It can be done anytime. It takes the precedence. As soon as I place a value of 0 on my preset, then basically it just forces Q to be a 1. Okay. And if I want to make sure that this operates as normal J&K flip-flop again, then I will need to go back and place a 1 on my preset. So this is how the preset and clear inputs work. And I can use them to build or to construct a counter that can count any of these random counts. All right, so let's see how we can do that. So now let's look at the design of a decade counter. So in other words, my flip-flop has to count from 0, 0, 0, 0, 0, 0, 0, 1, so on, 1, 0, 0, 1, and then on the 10th clock pulse, it should basically reset to 0, 0, 0. Okay, and then start counting back up again. So this is what I want to realize, a counter that can count in this fashion. And how do I realize this? Okay, now let's go back to the circuit, the ripple counter, but this time with the preset and clear inputs. Okay, and see if we can modify that and exploit the preset and clear inputs to construct this particular circuit. Okay, again I will use a ripple counter that contains 4 of these flip-flops, each flip-flop containing the preset and clear inputs. And each of these inputs are active low. Again, so when you're reading about anything, when it says active low, you know what that means. That is represented by the bubble circuit, and you need to apply a 0 input to make that input active. Okay, and if you don't want this to be active, then that means these have to be always at 1, at a high value. Okay, so that's my preset for each of my flip-flop, and these are my clear inputs. And I have to configure each of my flip-flop. This is my J D, KD, JC, KC, JB, KB, and JA, KA. These are all negative edge triggered flip-flop. That's the master clock. And that's my Q inputs, QD, applied as a clock. Oh, let me actually show this. These are all tied together, and I'm applying these to 1, so that these are configured as in the toggle state. QC, QB, that's it, and that's QA. QD, QC, QB, QA. All right. And now I want to configure these. Now, before we do that, again, so PST, just to make sure that we know, PST and clear. A 0, 0 should not happen. Does not make sense. You cannot have preset and clear both be active at the same time. So you should avoid that condition. That doesn't really make any sense. 0, 1 indicates that my preset is active. That means I'm forcing the values to be a 1 on my flip-flop. Preset is active. 1, 0 indicates that my clear input is active. That means I'm clearing. Clear is active. I'm clearing the output of the flip-flop. 1, 1 indicates that that's a regular JK operation, JK flip-flop operation. Okay. All right. Now, what do I need to do? I need to make sure that on the 10th clock pulse, so that's 0th clock pulse first, 9th, on the 10th clock pulse. In other words, I need whenever I get a count of 1 0 1 0, that's count for 10. I need to recognize that this is a valid count. I need to make sure that this count happens, and on the next count, I need to recognize the count and clear some flip flops, not all of them, so that I get a count of 0 0 0 0 on the 10th clock pulse. It makes sense? That means I need to clear some of the flip flop. Which one I have to clear? If this is QD, this is QA, QB, QC, and QD. What I need to do is I need to clear on the 10th clock pulse. I need to clear QA and QC. Right? If I clear them, then that means I get a count of 0 0 0 0 on the 10th clock pulse. Right? Okay. So how do I realize this? Well, I will use my clear inputs. I have the clear inputs there. Right? I will basically use the clear inputs to clear the contents of Q, what is it again? QA and QC. This is how I'm going to do this. I'll use an NAND gate. I will apply the value of QA. Again, remember that for a NAND gate, you have two outputs, two inputs A and B. Output is F, 0 0, 0 1, 1 0, 1 1. And every time I have a 1, only when both of these are 1s, then the output is 0. For the rest of them, these are all 1s for a NAND gate. Right? So that means I need to get a 1 here on the 10th clock pulse so that I can apply these to QA, the clear input of the QA, and QC. So that they are cleared. When I read this value 1010, I need to clear QA, QC, and for the rest of the times I don't have to do anything. So that means I need to get a value of 1 only when I have 1010 being applied to this gate. So what should we apply to this gate as inputs? That should be QA, QB prime, QC, and QD prime. Right, so basically I'm taking, so these values should be 1s otherwise, and these should also be 1s because I don't want to preset anything here. This should always be 1. Those are 1s, and this configuration allows me to obtain a count going from 0 to 10, up to 9, and then the 10th clock pulse, this reads as 10. I get an output of 1 here, which is being applied to the clear inputs of my QC and QA. That gets cleared to get me this particular value. And on the 11th clock pulse, again, these are all made inactive because the output of this becomes 0. I'm sorry. Sorry, this should be 0, not 1. Okay. So on the 10th clock pulse, the output becomes 0. And for the rest of the clock pulses, this becomes 1. That means these flip-flops are configured in their normal JK operation. Only on the 10th clock pulse, this becomes a 0. And then these two are active. They're cleared, forced to be cleared. And then it follows the cycle. So here's a counter that can actually count And you can do that for any arbitrary count, right? If I want to count, for example, from 0, 1, 1, 0 to 0, 1, 0, 1 and back to this count, you can also do this. Now, with this particular setup, where you have the clear and the preset inputs, I should be able to get any count I need by using the preset and clear, by using this kind of mechanism that 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 checks for the count and makes the appropriate output forced to be cleared or preset. Okay. All right. So let me take a pause here and let me see if you have any questions so far. Does that make sense? The concept behind this, the use of preset and clear. Okay. All right. And you should be able to do that for preset as well. In this case, I would like you to see, if I want to get a count from 0, 1, 1, 0, which is basically 6. Oops, wait a minute. To let's say 0. Let's say if I want to design something like this, from 2 to 7 and back to 2. So this count goes from 2 to 7 and back to 2. How should I design this? What kind of modification can I do here so that I can obtain this circuit? Can you suggest something? I want to obtain a count. So that means I need to recognize 0, 1, 1, 1 as my final count. Okay. The next count would have been what? 1, 0, 0, 0, right? Following 0, 1, 1, 1, the next count would have been 1, 0, 0, 0. That means I need to recognize this count and use my preset and clear inputs to obtain this count, right? So I need to recognize 1, 0, 0, 0. That is, again, this 1 corresponds to QA, QB, QC, QD, right? That means in this case, same mechanism. The only difference here is I would recognize 1, 0, 0, 0 in this way, so that when I apply 1, 0, 0, 0 here, only then I will get its value of 0. So here I will have QA applied as is, QB. Remember that for an AND gate, only when all of the inputs are ones, I get a 0 as the output. That's why that's QC, that's QD. Now, I don't want to clear all of them. I just want to clear some of them. That means once this happens, I want to clear QA, QB, and QD and preset QC. Clear QA, clear QB, and clear, what else do I need to clear? QA, QB, and QD, right? QD, which is here. I want to clear these. That means this is going to be a 1. And I want to apply a 1. I want to force the output of QC to be a 1 after that. So I need to basically force, once I recognize this count, I need to take this and force QC to be a 1. Like that. So now when this happens, when this particular count is recognized, I get a value of 0 here. I clear the contents of QB, QA, and QD, QB, QA, and QD cleared, and preset the value of QC. Preset the value of QC. That's how I get count from 2 to 7. On the 8th clock pulse, I go back to 2, count to 7, 8th clock pulse, go back to 2, and so on. All right, so that makes any count possible by using the preset and clear inputs. Okay. And so with that, let's conclude our session here. The next class or in the next week, we will pick it up from here. We'll talk about a few different types of counters and some of the issues with this ripple counter, and then we'll put the concept that we have learned so far, all of this together, and start building what are called the state machines. So we'll talk about state machines in the next week. Okay. With that, let me take a pause. Let me see if you have any questions of any sort here. Does that make sense? Okay. If you don't have any other questions, then let's conclude here.